Okay, so picking up where we left off last time, we were talking about the fundamental theorem of line integrals, and we had basically proved the result. The idea is that if you want to compute a vector line integral, and if, really importantly, super big condition, if your vector field is a gradient, which physicists like to refer to as being conservative. I like to refer to it as being a gradient. I think it's more direct and blunt, right? But if that's the case, then look at the handy, convenient formula you have for computing that vector line integral. We made an argument about accumulations. Again, that's one of the big themes, right, that you're going to notice in a lot of the theorems that we're talking about for these last few weeks of the course, chapters 6 and 7. Is there's always an accumulating quantity that we are basically adding up over the interior in all of these cases, appropriate to the context of what we're talking about. So what we ended up with, not going through everything again that we did last time, is that the total amount of change was this integral, and then that's where we ran out of time, as I recall. Okay, so let me pick up from there. I'm going to start by reminding y'all this is old news. We knew this a long time ago, that this is t times ds is just another way of saying the dx vector. So that allows us to rewrite the theorem like this. And so the question comes up, well, from this point of view, if I want to view this as a statement about densities, right? Usually we like to think of these theorems as quantity is an integral of some appropriate density. Can I view the gradient as being a density? And the first answer that's going to occur to you is, no, that doesn't make any sense. It's a vector. Densities are scalars. Right? So, okay, that's a legitimate complaint. So let me remind you that we have already exercised some flexibility with the idea of the word density and what density means, right? And of course, everybody comes into this course with the idea that density is mass specifically per unit volume specifically, right? We've already been flexible that, hey, it might not be mass, it might be population, it might be something else, it could be any accumulating quantity. And likewise, it might be volume, but it might be area, it might be length, who knows? There's, whatever the appropriate notion of size. So now I want to introduce another kind of a flexibility, and that is that the size might be what I'm going to call an oriented size, which is let's see here, I'm kind of, forcing it in some sense, right? It seems like maybe a little bit of an unnatural choice, but that's kind of what we're looking at here, right? The dx vector kind of is like a size. Its magnitude literally is a size. Its magnitude is ds. That's a size. But in addition to the magnitude being the size, this also has a direction. The direction is telling you how is that size oriented, you might say, in space. So I think the idea of calling this an oriented size is not that big of a stretch. And with that tolerated, perhaps, bought, hopefully, it's more reasonable to think of the gradient then as being an oriented density. So in the sense that this relates to quantity by way of an oriented size, and so it's an oriented density. So it's just a point of view. It is a nice interpretation of the gradient, and you could say that this is unnecessary, and we don't really need to take these points of view, but just a little bit of foreshadowing. Looking ahead, we're going to see another theorem coming up in the next week or two, where we're really going to need to make an interpretation of a vector-valued integrand somehow geometrically, and you need to make some sense out of it as being a density of sorts, and the best way to make sense out of it, frankly, is to think of it as an oriented density relating to an oriented size. So think of this as a starter example, and we're going to kind of build on this with a more sophisticated example later. Okay. All right, so let's do one. Here again is our theorem. when your integrand is a gradient. If you find yourself needing to compute a vector line integral, then cool, you can rewrite the question. You can answer the question just by computing this expression f of b minus f of a. Okay. All right. Now, very importantly, notice, in order to use this theorem, you're going to need to know what that function is whose gradient is your vector field. Specifically, you're going to need to know what I like to call the anti-gradient, right? You may remember I introduced that term back in chapter 3, anti-gradient. And the reason you need to know it is because you can see right there, that's the function that you're going to be plugging the endpoints into. That is but in some sense, most of the work of one of these questions is finding what that anti-gradient is. And we'll talk later about how to actually do that. But let's get one into the win column here. Question is to compute a vector line integral. Quick pause before I go into the solution. I want to point out something about the way this question is phrased. Notice this question just says compute that thing. Right? This question doesn't say, here, use the following method. Right? It just says, here you go, compute it. And you get to decide what method you want to use. Now, choose wisely. Right? You don't want to choose some method that's going to make the problem intractable or unnecessarily difficult or something like that. Now, the way this question is phrased, here you see that the parameterization is given, and that might psychologically kind of push you toward using the parameterization, namely pulling back through the parameterization, namely the usual plug-in chug. Right? But notice if you do, x is cosine, y is sine. That means that this vector field is actually going to be a whole bunch of stuff, right? There's going to be all sorts of trig involved if you pull back through the parameterization. Which we could do, but all else being equal, we prefer not to. Okay. All right, so what I'm going to do instead is try to make use of a different approach, and the key insight is this right here, and that is that our vector field is a gradient. Now you can confirm directly. When you take this function x squared y squared, compute its gradient, you get exactly that vector field. That means that our condition is satisfied here. Our integrand is indeed a gradient. Everybody happy? All right. So, too far. Here we go. Okay, so that means that this function right here is our anti-gradient. That means that's the function we're going to plug into. You can see it right here. That's the f. I just need to plug in the starting point and the ending point. The starting point, of course, comes from plugging in t equals 0. That gives us our a. And the ending point is going to come from plugging in t equals pi. And that gives us our b. That's just arithmetic. And by the way, now this process of plugging in the bounds for the parameter into the parameters, that's just how you find the endpoints with a parameterized curve. Other curves might be described in different ways, and the way you would find their endpoints are going to be different, appropriate to what it is that you know about your curve. This is just how it works out in this particular case. And then it's all over but the arithmetic, and that integral, f of b minus f of a, answer turns out to be 0. Much easier than dealing with trig integrals. How we doing? Everybody on board? All right, so we'll talk later about something that I just glossed over. Namely, I was so happy at the very beginning of this example to say, hey, check it out. Look at this. Our vector field is a gradient. And a reasonable question might be, yeah, well, how did you know to entertain that function? Where did you come up with this anti-gradient? Very reasonable question. We will talk about that. It'll just be later, probably not quite today. We'll get to it on Friday. Okay, but we will discuss that. Okay, before we do, we're going to move on to a different thing. We're going to talk about this idea called path independence. This is I'm going to say a surprising property. The first time I saw an assertion that there existed vector fields that had this property, I wasn't sure I believed it. It seems kind of crazy. So let me talk through what it means for a vector field to be path independent. A vector field is path independent if, whenever you have two curves that have the same starting and ending point, so they both have to start at the same point, they both have to end at the same point, and I'm going to entertain, for example, one curve that starts and ends appropriately, thinking about its line integral. Then I'm going to look at another curve, same starting point, same ending point. I'm going to think about its line integral. Right? The idea is that a vector field is path independent if, as an integrand, it makes these two integrals always equal, no matter what curves you pick. Now, again, I think that sounds outrageous, right? You're telling me I can pick any curves I want? Any curve? You think about how many different curves there are that start at that point and end at that point. There's countless, right? I could take one that goes up and goes around in a circle several times and then comes down, or endless different curves. How could they all give you the exact same value for the line integral? Notice this green line integral only looks at what the vector field is doing on the green curve. This blue line integral looks at the vector field in entirely different places. And yet, again, we claim that these integrals are always equal. It seems like a lot to ask, right? Now, just to support the suggestion that this is seemingly unlikely, and by the way, I emphasize, rare that this happens, right? Most vector fields are not path independent. So here's just kind of an easy little sort of generic, pulled out of a hat, unmanufactured example. Let's think about this vector field right here that I've got a picture of. You want to think through, what that picture looks like. Persuade yourself that you believe that this is what that vector field looks like. So let's just pick a couple of random curves then. We're going to pick a couple of curves that start at the origin, end at 1, 1. Right? So two curves with the same start, same end. We're going to think about that green curve, and we're going to think about this blue curve, and let's just see what happens. Okay, each one of these, of course, has two legs. We'll start with the one, this sort of first leg of the first curve, and notice the vector field is just flat, 0, all the way along this first leg. So on that first leg, you're not getting any line integral at all. And then on this second leg here, different sort of coincidence happens there. There, the vector field is straight up, but the dx vector along this piece of curve, dx vectors are all horizontal, and so this dot product, f dot dx, well, that's vertical dot horizontal, that's going to be 0. And so, in fact, altogether, on this first curve, on C1, on that curve, we get 0. Yeah. We don't have to parameterize things. We can just kind of piece by piece just see that that's going to give us 0. Okay, now let's look at the second one. Let's look along that. Again, the first segment of C2. Well, again, we have this perpendicularity. The vector field is up. The dx vectors are straight to the right. Again, the dot product is 0. Again, we get nothing. And then here's where it gets interesting, though. If you look at this second leg here, on that second leg, the flow is upward. The dx vectors are upward. There is a significant extent to which this flow is along the curve. We're going to get positive line integral on that second curve. And you could work out the details if you want, but not necessary for this example. The punchline, though, is that, missed. On this second curve, the integral is positive. So, again, this is what you would kind of generically expect. Even if the curves start and end at the same point, well, that's just the start and the end. For most of these curves, they don't even touch each other. Completely different curves, you should expect to get different values along these different curves. So this is most of the time. Right? Okay. All right. Now that hopefully I have you persuaded that path independence is at best rare. Let me show you that not only does it happen, it happens regularly in a special circumstance, and that is if your vector field is a gradient, then it is path independent. All gradients are path independent. By the way, there are some regularity issues that we do have to worry about. I don't want to worry about them here. We're mostly not going to worry about them in the course. But you'll notice I do have continuous written here. That means I need for the vector field being the gradient, I need that to be the case everywhere. There can't be any missing points. It really does mess things up at different points if we have a problem like that. Okay, so no irregularity issues. I am, as previously discussed, going to set a starting point and an ending point, and now we will think about this first curve here. How would I compute the integral on that first curve? By the way, let me take that off for the moment. Notice that we are taking an integral of a gradient. Right? On this first curve, my integrand is f. F is a gradient, so I'm looking at an integral of a gradient. We have an awesome theorem somewhere. If you're doing an integral of a gradient. If you're doing an integral of a gradient, right? Fundamental theorem of line integrals. F of b minus f of a. Right? Awesome computational tool. So I'm going to rewrite this green line integral as f of b minus f of a. Notice that f of b minus f of a is computed by only looking at b and a. It's computed only looking at those endpoints, those shared endpoints. So now, analogous argument on C2. On C2, well, again, we're talking about a gradient. Again, we're computing a line integral of a gradient. Again, that means we can use the fundamental theorem of line integrals. Again, the formula is f of b minus f of a. Again, computed only looking at those shared starting and ending points. So, really nice punchline, right? These two integrals, looking back at the picture over here, the blue integral and the green integral, well, they're computed by using the same formula on the same starting point and the same ending point. So no surprise, yes, you do get the same answer, and therefore path-independent vector field. What do you think? Everybody see the argument there? It's real clever. Really clever observation. Okay. So there is a sort of another version-ish, you might say, of this statement. So what we just showed is that gradients are path independent. The statement goes the other way. Again, regularity issues ignored at a minimum for this first cut through. Not only is every gradient path independent, but every path independent is a gradient. Said differently, every gradient is path independent, and only gradients are path independent. Again, ignoring regularity issues. Okay. All right. This second sort of half of the statement here, this right here, it's a little bit harder to prove. I'm going to give you a sketch here. You don't have to fill in these details, but if you'd like, if you're curious, this is a push in the right direction. You can, play with it, try to fill in the blanks. If you get stuck on this, come talk to me. I'll be very happy to help you through it. Again, you don't have to. This is not part of the course. Okay. All right. Here's a different point of view. By the way, y'all will probably remember there's various different points in the past where y'all have seen definitions that could be made in different ways. Like if you look back at the definition of E, do y'all remember the definition of E from way back in single variable calculus classes, possibly algebra classes? There's like 6 of them. They're all equivalent, right? They look different, but they all define the exact same number. And likewise with various other ideas that y'all have seen here and there. So this is going to be, again, a sort of an alternative definition, different point of view on the exact same idea. And we're going to get to this by starting with what we had in the first place, namely to agreed upon start and end, 2 different curves that have the agreed upon start and end. Looking at the blue integral, looking at the green integral, path independence means that these are always the same. Cool. Now, easy algebra shows us this right here. Right? Easy algebra shows us that they just subtract the blue term to the other side. That means this difference is 0. Now, let's look at the difference. Let's look at the green integral minus the blue integral. Let's think about what this looks like. Green minus blue. Keep in mind, minus means you're going to move along that curve. You just with the minus sign, just can be thought of as representing you're going to go the opposite orientation. You're going to go backwards along the curve whose integral is minus. So think of this as moving along C1 and then subsequently moving backwards along C2. And that gives you, here's moving along C1, and then now I'm moving backwards along C2. Notice what that gives me is a single line integral that starts at this point and then kind of goes all the way around and comes back to the exact same starting point that it started at. It ends where it started. In other words, it's a closed curve. So what we have here then, now throwing away all this stuff that we started with, we have sort of an alternative formulation of path independence. A vector field is path independent if these closed line integrals, like so, are always 0. It's a different way to go. Okay, is that good for everybody? Are y'all good? Any questions? No? Okay. All right. So what's this good for? Having different definitions or different ways to phrase things can be useful in different cases. Here's a nice application of this closed curve point of view on path independence. Y'all may recognize, some of y'all anyway, may recognize this piece of artwork here. This is by an artist named M.C. Escher, and he did a lot of different things, but among others, he made sort of artistic illusions. So this drawing, you'll notice, is vaguely realistic looking, right? It's not like it's an abstraction or something, and yet, even though at a quick glance it looks like, okay, it's a picture of a building, and there's some stairs on top, and there's some people walking on the stairs. The more you look at it and think about it, you realize, wait a minute, they keep walking around in circles, and they keep coming around to right back where they had been, and yet they also, these people on the outside anyway, all seem to be walking consistently uphill. Wait a minute, that doesn't make any sense. Right? You can't do that. And likewise, the people on the inside, they all seem to be walking downhill. So it's interesting to be able to draw something like that and make it look plausible, even though, of course, it's physically nonsense. It's absolutely impossible to do that in the physical world. So what I have up here is just a sort of a mathematical take on why that's nonsense. So let's look at this vector field right here, the gradient of the altitude function. I like to think of this as the steepness vector field because, of course, gradients always point uphill, right? Chapter 2. And the magnitude always tells you how steep. So, just a word. But anyway, it's clearly a gradient. As we discussed, gradients are always path independent. And path independence can be formulated by this observation that all closed vector line integrals have to be 0. Okay, now what does that have to do with the Escher stairs? Well, let's think for a moment, real quick moment, about what do the terms in this line integral represent. What does f dot dx mean? Keeping in mind that f is the gradient of the altitude function. So this really means gradient dot dx. That means that each term here represents, as these people take steps, as every sort of step they take, how much does their altitude change? Right? And according to the picture, as Escher has it drawn here, each one of these people on the outside, every step they take increases their altitude by at least a little bit, a positive amount. Right? So the integral then is adding up a bunch of positive terms as they go around. Escher, as he has it drawn, would have us believe that it is possible for all of these terms to be positive. But path independence tells us no, that is not possible. Path independence tells us these terms have to add up to 0. So some of them are positive and some of them have to be negative. So I think this is a nice point of view on why it is that this is an impossibility. That makes sense to everybody? It's not that you need the math to realize that this is impossible, but the math is a nice way of stating it. Okay. All right. Okay, moving along. So path independence is useful in a lot of ways. Real quick, I want to make a very. I'm going to try to restrain myself here, keep this as tight as I can. But path independence is really useful in a conceptual way in physics and in other ways, I'm sure. So specifically, path independence ultimately is necessary to make a definition of what we call potential energy. Right, now, if you haven't had a physics class before, no worries. Doesn't matter. This isn't a physics class. But if you want to make sense out of the idea of potential energy, you need path independence. Do we really need potential energy? Well, I say, but yeah, it's actually a really useful idea. Y'all may recall from physics classes, mechanics specifically, that potential energy is part of the two-term summation kinetic plus potential that gives you conservation of energy, right? And the fact that energy is conserved as mechanic things happen is a very powerful computational tool. It lets you compute the velocity of the blah blah, roller coaster, or, how fast is it moving at various points, whatever. Conservation of energy is a very a useful computational method. So path independence lies underneath all of that. You can't make sense out of conservation of energy without potential energy, and you can't make sense out of potential energy without path independence. So it's a conceptual contribution. That by itself isn't really a computational tool. It's what it produces are a computational tool. That said, it is sometimes computationally useful, but if you think about it, if you have a path-independent vector field, it is a gradient, which means you could just use the fundamental theorem of line integrals in most cases. So again, that's do we really need it as a computational tool? Why don't I just use the fundamental theorem? We already know that's awesome. So do we really need two different ways to solve a problem? And, sometimes. Here's the sticky wicket. In order to use the fundamental theorem, you do need to be able to find the anti-gradient. And there are some instances in which finding the anti-gradient can actually be a problem. That can be hard sometimes. So it is always good to have a plan B, and that's what we're going to see here. So here is an example. You'll notice vector field right here. I claim that that's path independent. I'll reveal in a few minutes how I know that. For the moment, I'm just going to assert that it's path independent. Now, of course, being path independent, we know it's a gradient. In this case, you could totally find the anti-gradient. You might even be able to kind of see it yourself already. If you can, cool. If you can't, don't worry about it. I'm going to show you the method in a little while, but probably not today, but I'll show you the method on Friday. Anyway, let's pretend that we can't find the anti-gradient, that I can't use the fundamental theorem of line integrals. How would I answer this question? Question being, looking at the top half of the unit circle oriented clockwise as I've drawn there, how would I compute this integral? Well, gosh, again, you could parameterize and plug in, and you're going to have a lot of trig, and we don't want that. Okay, so I'm going to use the path independence. Path independence says as long as I nail down the starting point, as long as I nail down the ending point, I can replace this given blue curve with any curve I want. Any curve I want, right? So, if I just to be a weirdo, I could say, hey, I can use that curve. Perfectly fine. And if you want to compute on that green curve instead of that blue curve, go ahead. Perfectly fine. It's got the same starting point. It's got the same ending point. Go for it. Obviously, I'm not going to pick that curve. Obviously, I'm motivated by the desire to make my life convenient. The most convenient curve that goes from the given start to the given end is that green curve right there. And path independence says that I can do this. Path independence is the thing that allows me to trade the blue curve for the green curve. And with that settled, now I don't need the blue curve at all anymore. We're done with the blue curve. Because of path independence, all I needed it for was the start and the end, and now I get to pick my favorite curve to use instead. So, this problem now, computing on the green curve, way easier. Way easier. Look how easy it is to parameterize. Right? That's awesome. Look what else happens, and this is pretty sweet. It says right there that the y-coordinate is always 0. That means that y right there is always 0. That means that this whole first coordinate of the vector field is 0 along my entire C2 new curve. Right now you can just see that right here in the picture. As I go along this curve, y is just flat always 0. It wasn't on the original curve, right? This is a awesome convenience that I get from having made a clever and appropriate choice of my method. And even better than that, notice further, all of my dx vectors are purely horizontal. Said differently, the y-coordinate of my dx vector. In other words, my scalar dy, 0. Again, right there in the picture. That line is horizontal. So dy is 0. And that means that my dot product here is just obviously 0. Immediate. Just dot that out. You get 0 plus 0. That is 0. And our answer is 0. And we didn't have to do any real labor at all, hardly. Path independence turns this from a difficult problem into an easy problem in one step. How's that? Anybody all right with that? Okay, so now back to what I swept under the rug. I made this assertion out of nowhere. I just claimed that this vector field is path independent. Where did I get that from? Was that a... yeah, go ahead.
Yeah, I was just going to ask.
Yeah.
How often do you see you working out this nicely?
As nicely as I have it here?
Yeah. Like where this is like a functional way to solve.
Yeah, I mean, most of the time that you're going to compute a line integral like this, most of the time you would just find the anti-gradient and use the fundamental theorem of line integrals. I think that'd be the easy way to do it here. I mean, the anti-gradient is pretty free. It's x squared y, right? It's no problem. There's a few instances. I like 10 years ago, I went through a sort of a phase where I was putting a bunch of such questions like this on my exams. And so you can look back through there, and I found I manufactured, highly artificial, right? But I manufactured some bonkers difficult vector fields that would be horrendously just absolutely intractable, unless you notice and cite the path independence. That turns them into trivial, easy problems, right? So it does. It happens, but in practice, in the natural, probably not very much.
Okay.
Yeah. Right. Yep.
Do you mind clarifying how you got x of t equals t?
Yeah, sure. There's different ways to parameterize this line here, right? One thing you could do is write down this point, and use the chapter 1 methods. With the difference is, b minus a is your direction vector, stuff like that. What I did here is I just observed that, look, I mean, y is obviously 0.
Yeah.
And so I put the 0 here. And then I thought, well, I need now some function to represent that I'm going to be moving to the right.
Okay.
And I just thought, okay, well, I guess I could just call that t. So I just kind of wrote it down. Yeah, that's right. But there's, if you had done it following chapter 1 methods, what you would have gotten would be just as good. Yeah. Right. Anybody else? Okay, so how did I know that this was path independent? Or more to the point, how are y'all going to know when you're looking at a vector field, how will you know if it's path independent? And here's the theorem. There's actually 2 versions of this theorem. We're going to start with the 2-dimensional version of this theorem. And here it is, the 2-dimensional version of the theorem. If you want to know if your vector field is a gradient, here's what you do. Compute Green's operator and see if you get 0. That's it. If you get 0, by the way, I don't mean 0 sometimes. I mean if it is flat, identically 0, then yes, you're talking about a gradient. And if it is ever non-zero, then you are not looking at a gradient, and it is not path independent. Okay, now how do I know that works? So where does this come from, right? What's the reasoning here? Here's the idea. You're going to notice first off that these 3 conditions that I have written down here are already noted, right? We already know that gradients are path independent, which can be phrased as closed line integrals are 0, or if you prefer, circulations are 0. Keep in mind, closed line integrals are circulations. Okay, so we already know those are the same. Okay, now I want to look at these 2 conditions. Why is it that closed line integrals being 0 would mean that double integrals of Green's operator must be 0? And the reason is ultimately Green's theorem itself, and you can just see it right here. This is Green's theorem. Green's theorem says closed line integrals, of course, now if you have a curve that starts and ends at the same point, then its boundary at some region, right? Boundary circulation, in other words, is a double integral of Green's operator. That's just what Green's theorem tells us. So this, the condition on the left here, this integral being 0, well, if that integral is the same as this integral, means that this integral must be 0. Okay. All right. Lastly, let's look at why these 2 conditions are the same. This one is a kind of a hand-waving argument, but it centers on looking at this integrand here, Green's operator. But the fact that this is Green's operator, that's the distraction for the moment. What this condition down here says, we have a function that I have highlighted in orange there is a function there, and apparently all of its double integrals, no matter what domain you pick, every double integral always 0, no matter what domain. How is that possible? Right? What functions can you think of, right, that will always give you an integral of 0 no matter what domain you pick? Can you think of any other functions that would do this? And no, in fact, you can't. There is only one way that that's possible, and that is if that function is itself 0. Everywhere. So that's the argument. It's a real clever little argument. It's valuable because it turns what I'm going to call a hard global question. I need to find a single function f whose gradient is the given vector field everywhere. Right? That's in other words, it's not good enough to find some function whose gradient is the vector field at one point versus a different point. I've got to find a single function that does that everywhere. That's a hard problem. But I've turned that now into a relatively easy problem of I just need to compute Green's operator. That's just a plug and chug. You can plug in any point you want. Plugging in one point, plugging in a different point, yeah, whatever. They're all kind of independent. You just have to make sure that you get 0 at all those points, again, independently. Okay. All right, so thus the term a local test. Okay, so now last little bit of terminology. Let's look at Green's operator here. Let me remind you what Green's operator is. And again, there's a bunch of different ways to think about it. But the one that I like to push is that Green's operator is circulation density. Right? So circulation means to what extent is the fluid kind of flowing around, as you go around a closed loop. Right? Circulation density means as you look smaller and smaller, how much of that sort of rotation of the fluid can you sort of imagine happening, in the vicinity of a single point, right? So Green's operator measures the extent to which the fluid has a rotation in it. Okay, so Green's operator measuring rotation. So saying Green's operator is 0, I think it makes sense to call this irrotational. And that's, again, a pretty standard term. Maybe not as common as conservative or gradient, right? But nevertheless, it's a very communicative term. I actually like this term quite a bit because it explicitly describes exactly what this condition here says, that Green's operator must be 0. So so rephrase, and again with regularity issues aside, gradients must be irrotational. Okay. All right. Now reminder, that's in 2 dimensions. There is a separate theorem in 3 dimensions. And good news, they look almost identical. Here is the theorem in 2 dimensions. Here now is what I'm claiming is the theorem in 3 dimensions. The only difference, practically the same, the only difference is that where it was Green's operator that I compute with in 2 dimensions, it is now curl that I compute with in 3 dimensions. Same idea. How does the argument work? Well, that's where things do get a little different. This argument that I made up here, there is an analogous argument, but the analogous argument requires using a theorem that we don't have yet. We'll get there. We will. It's called Stokes' curl theorem. You've probably heard of it, right? When we have Stokes' curl theorem, we'll be able to make this argument down here. For the moment, I'm just going to ask you to take my word for it that it's highly analogous, and we are going to eventually prove that. Okay, so let's actually do one. Let's look at this vector field right here. Try to decide, is that or is that not a gradient? In other words, is that or is that not path independent? First of all, notice we are in 3 dimensions. Oh, I really need to clean up my mess. here. We're in 3 dimensions because you can see we have 3 coordinates to our vector field, thus 3 dimensions. Thus, I need to look at curl. So let's start computing curl. And this is just a matter of plug and chug. We have formulas for curl. By the way, do please take a minute to go back to chapter 3 and remind yourself of that formula for curl. You need to have that memorized. You need to make sure that you can, in practice, compute curl when necessary. And here you go. What you end up with is 3 coordinates, because curl, of course, is a vector. And notice I kind of stopped the computation after the first coordinate. Why did I not compute the second and third coordinates? Or did I just give up? Right? What happened there? Well, keep in mind, what I need to know about curl. I don't actually need to know the whole curl. I just need to know, is it uniformly the 0 vector, or is it not uniformly the 0 vector? And the thing is, I'm actually already resolved. After the first coordinate, I look at this first coordinate, it's not identically 0. Game over. Does that make sense? You don't have to compute the second and third coordinate. You can if you want, right? But you don't need to, because non-zero first coordinate means it's not the 0 vector. Just to be clear, had this been 0, I would have had to compute the second, and then if that was not 0, I'd have to compute the third, because just having a single coordinate be 0 doesn't guarantee the others won't be non-zero. So this is a one-way convenience, you might say. Okay, so curl is not 0, so it's not a gradient. Game over. Analogously, let's look at this next question. Here is a vector field. Y'all may recall this vector field. It looks like this. We talked about this early chapter 6. Late chapter 3, I guess it was. Right? We've drawn that picture before. So let's ask, is that a gradient? And again, we have a computational tool for this. The way we decide if something in 2 dimensions is a gradient is we compute Green's operator. So blah, 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 details. Not 0, so it is not a gradient. Is that all right? Everybody happy with that? Just plugging straight into the theorem. All right, now I'm going to say that I find this to be a very satisfying example because, again, you look at this vector field. Here again is our picture of this vector field, and you can kind of think this through sort of geometrically. Looking again at this question, is this vector field a gradient? Well, keep in mind, gradients have special properties. Gradients always point uphill, right? If this were a gradient, then all of these vectors would have to be pointing uphill. What kind of a hill is that? Right? Where this is what uphill is doing. It doesn't make any sense. There is no such hill. Right? You can't, in other words, start here and go uphill, 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 keep going uphill, still going uphill, continuing uphill, and et cetera, up, and then end up right back where you were in the first place. Nonsense. Not possible. One way to say this, gradients cannot have circulation. Because uphill can't come back around on itself. Okay. All right, so again, satisfying. I mean, we have this algebraic test that tells us no, so it's also satisfying to see geometrically that it's, of course, obviously a no. Okay, all right, so let's see here. Last thing, actually, how are we doing on time? Oh, no, we are out of time. We have 15 seconds. Okay, we will pick up here next time, Friday. Y'all have a good rest of your Wednesday. See you later. Don't forget to let me know if you came in after I did attendance.